Yeah, so whenever you're ready, feel free to take the stage. And I can see your screen.
All right. All of the Zoom controls dialed in. All right. Hi, everyone. My name is Nick, and I'm here to talk about the 2 million container challenge. This is something we performed and published some results of a few weeks ago, and I want to dive in and kind of get into some of the nitty gritty details about it. So like I said, my name's Nick Ethier. I work as an engineer on the Nomad team at HashiCorp, among other things. And before we jump into the C2M challenge, I think it's a good idea to talk about its origin story. About 5 years ago, actually 5 years this month, we published the results of a C1M challenge. So this is where we did 1 million containers. And this was, 5 years ago is quite a long time in software lifetime. This was 10 major releases of Nomad ago with our 0.3.1 release. And just to give you an idea of some of the setup details as we go into C2M, this used 5,000 nodes running in a single region, and all of those client nodes were the exact same instance type. It was a homogeneous cluster. And with that, we were able to schedule all 1 million containers onto this cluster in just under 5 minutes, which we felt was a pretty great accomplishment. So as we move into talking about C2M, the detailed results are all online, hashicorp.com/C2M. But I want to focus on, some of the reasonings of why we made some different decisions in the test setup process, and give you some of my interpretations of these results. So we ran this using the latest major release of Nomad at the time, which is 1.0.1. We ran this across just over 6,000 nodes. And you might expect the node count from C1M to C2M to double. And we'll get into why that didn't actually happen. It's also of note that this was a heterogeneous cluster of nodes. So there were various different types of nodes in this cluster. And this sort of also lends to why there was such a fewer node count. We were able to get some larger nodes, which packed more allocations onto them, which ultimately brought that count down. And this was deployed across 10 cloud regions, really all around the world, utilizing Amazon as our partner for this. And we were able to complete this challenge in just about 22 minutes. Now, we expected it to be longer than 5 minutes from the previous challenge, but I think 22 minutes was a pretty fair result, and we'll get into sort of why that was. It was, if you compare to how many scheduling decisions the scheduler made per second, it was quite a bit slower than our first test run back in March of 2016. But I think there's some really good reasons as to why. So to sort of understand those, let's look at all the changes that Nomad went through from 0.3.1 to 1.0.1 that we ran this test with. So here are just some very quick Git stats from the Nomad source repository. You can see that there was, over 2 million line insertions from that version to now, which is maybe not a good representation of all the changes, since Nomad also includes vendor dependencies and things like that. But we can look at just the scheduler subdirectory, because that includes all of the code for our internal scheduling library. The way that a Nomad server works is it uses this scheduling library, and it gives it access to the state of the cluster and the job it would like to place, and it sort of spits out a scheduling decision. And that had some pretty considerable changes over the last 5 years. But I actually dove into the code at 0.3.1 when making these slides. And the structure of everything is actually very similar. We were able to add features and enhancements onto sort of the original design of the scheduler without having to go through any major refactorings or major rewrites of the scheduler, which sort of, I think, speaks volumes to that original design. I wasn't working on Nomad at the time, but it's always interesting to see how things evolve over time and how sort of the initial assertions and design goals of Nomad are still very present today. So to get an idea of what actually changed in that scheduler package, let's talk through a very simplified overview of how the scheduler actually works when it's trying to find a place for work in the cluster. There are really three phases that the scheduler goes through. It iterates through all the nodes in the cluster. In this first phase, we can call feasibility checking. And this is sort of the cheapest logic computationally that we can do in scheduling. And the idea here is sort of eliminate as many nodes as we can, as many options as we can, or throw the node out as early in the scheduling process as we can, so we can save the more computationally expensive logic for nodes that require it. So these are things like constraint checks. If you have a job that says it must run or not run on a node with some node metadata, or if you have a distinct jobs constraint or a distinct node constraint. Other things are things like each node reports the drivers that it has and their health associated with them. So we'll throw out nodes that don't have a healthy Docker driver running if the job requires Docker, or if the node has been marked ineligible, maybe it's draining, or for what other reason, we'll obviously throw that one out. So if we move on to sort of the next phase, once we've passed this feasibility checking phase, we move on to fit testing. So this is where all of the resource accounting is done for the scheduling purposes. This is where we pull all of the allocations that are running on this option that we're looking at, this node that we're thinking about placing on. We grab all the allocations and we combine all of the resources together. So we get a total number of used resources on that node. And then we take the resources that are requested for this job and combine them. And that total there is our proposed allocations, or our proposed total resources. We check and see if that new total will fit on the given node. And by resources, in 0.3.1, this was really just CPU and memory. So two different dimensions of resources we had to look against. Over the years, we've added more resources that are sort of tracked by this, things like port mapping and host networks. So we're trying to track port allocations all over multiple IP addresses potentially. We also have device plugins now, which can report resources as well dynamically. So we have these dynamic device resources we have to check against. And a couple years ago, we added preemption to Nomad. So this is where preemption ticks in. If that total combined resources won't fit on the node and preemption is enabled, then the schedule will work through at pulling allocations out of that proposed list that are of lower priority until that proposed set of allocations will fit on the node. So all this sort of happens in fit test, and it's really our most computationally expensive part of scheduling. To visualize that, we'll look at a flame graph here. So if you're not familiar with this, this is called a flame graph, and this is of the CPU profile. And the way a flame graph is sort of read is you can look from the top to bottom, and these are the call stacks essentially. So if you have a function that creates multiple go routines or threads, those will branch into multiple stacks underneath, and each subsequent call is another line in this call stack. And then the width of those lines sort of describes the amount of time that they were spent utilizing CPU for this profile. So in this sort of measuring cup looking flame graph, we can look and see that the cup part of this all the way on the left, that big chunk is all of the scheduler. That scheduling library is using about a third of the CPU time during this profile. And then the rest of this are other things the servers have to worry about. There's a small chunk for the RPC request handling. All 6,000 of these clients are reporting heartbeat and health checks back to the node, and those have to be handled. And everything has to be stored, and we have a Raft state store, and there's a small chunk handled for that. And then sort of the tail end of this on the right is really just the Go runtime garbage collection, other things like that. But let's jump in here to the meat of this, the scheduling portion. So I zoomed in here, and what I wanted to highlight here, I've got some things underlined in blue, and those are the main functions that are called in this fit test. And you can see probably 90 to 95% of time spent running the scheduling operation is done just in that fit test section. And actually, just to show how computationally cheap that feasibility part of that is, that there's a little, all the way on the left, there's a green arrow and a tiny green box. And that highlights the tiny sliver of function calls, the amount of time that those function calls took as compared to everything else. So this is why we try and get that node thrown out as early as possible before we move on to doing these sorts of expensive fit test operations. All right, so we've got a node. It's feasible. We know the allocation will fit on it. But there could be other nodes where that allocation fits on. So this is where the final phase in this scheduling process comes in, and this is scoring. So once a node has been scored for an allocation, the scoring is things like we can score based on the bin pack or the spread. This allows us to sort of bias scheduling decisions towards packing allocations onto the smallest set of nodes or spreading it out over as many nodes as we can. That's one of the scores. We can also score based on configured affinities or anti-affinities even. These are kind of like constraints in that you can say, a constraint can say this job must be placed on a node with this metadata. But an affinity is just a bias or a preference. You know, you would prefer that your job runs on a node that's marked as, you know, a high performance node or something. And then the other score that we get is for rescheduling penalties. If an allocation for some reason needs to be rescheduled, maybe it failed on a node or it was preempted, we actually penalize that node when it goes back through the scheduler so that we can avoid rescheduling back onto the same node that might have had a problem. So all of these scores get normalized together into a single score. And that's how we can compare two scheduling decisions. We can, you know, we have a node or an allocation can fit on one of two nodes, and we want to pick the best decision. So this is what gives us our scheduling mechanism in Nomad. And what this yields at the end of this challenge is this nice graph here that shows our climb up to 2 million running containers. And what's really nice to see in this graph is that it's linear. It was linear in C1M as well. So it was really exciting for me to see that over that 5 years of adding new and great features to Nomad, adding and enhancing the scheduler, we are still a very linear growth in terms of, you know, the number of operations being done in the scheduler. We haven't introduced some bug that only manifests itself, you know, when we're at these high scales. That was really exciting to see. So let's move on and talk about the infrastructure that this test ran on. Like I said before, we partnered with Amazon Web Services, specifically with their EC2 Spot team for this test. If you're unaware of EC2 Spot, it's a product that AWS offers that allows you to buy spare capacity of instances up to you know, a 90% discount even on their pricing and run them on AWS's cloud. Now, the caveat here is that this is spare capacity. So as demand increases, that capacity can shrink, and your instance could be terminated in favor of those higher on-demand or reserved instance types. So we wanted to sort of push this idea to the extreme, which is why we deployed this on 10 different regions in Amazon. The idea being that we could take advantage of spare capacity in as many regions as we can to try and lower the chances of incurring one of these interruptions during the test. And during the test, we actually had no interruptions, which was really exciting to see. Now, this sort of is an atypical Nomad deployment, I think, that most people think about, because Nomad does have a you know, multi-region built-in, you know, from the ground up by default. But we didn't utilize this in this test. We just created one single global region and had each of these cloud regions all connect back to that single region and US East. And so you might be thinking, why not utilize that great feature of Nomad? And really, this is because if we were to do that, use multi-regions, each region in Nomad becomes its own scheduling boundary. So in essence, if you had two regions in Nomad, they would be scheduling independently and concurrently of each other. It would be like showing up to a race with two cars and saying that, hey, I can beat everyone else because the combined distance of my two cars will be way farther than anyone else in the same amount of time. So for a fair comparison, this is why we stuck with one region. So how did this actually work out? We had all of these clients connecting back to this central region in US East. So to secure this, we utilized Nomad's MTLS capabilities. So the servers in this had a public IP address exposed to the internet that was authenticated through TLS, and all of the clients were able to connect to that public IP. And what's really interesting here is these clients actually ran in VPCs on Amazon with private IP addresses. So the clients themselves didn't have public IPs. The workloads on them didn't have public IPs. But we utilized NAT gateways to NAT out to the public internet and be able to connect back to Nomad. Once these clients establish a TCP connection over TLS to these servers, they can keep that connection open. And that's how the server is able to communicate into those clients to make RPC requests or anything else that it needs to do. Obviously, this is not a recommended production configuration, but it sort of gives you an idea of how flexible Nomad can be for any sort of network or infrastructure topology you may have. So I mentioned that we ran this on AWS Spot. In part of doing this, we tell AWS Spot through our Terraform configuration that we'll accept an instance being placed on a large variety of different instance types. And what we were actually able to do is weight the instance type by how much memory they had. This is because we kind of had a mental idea of the memory overhead each allocation had on a machine. So we can extrapolate to 2 million plus some overhead and get an idea of, we need X terabytes of total memory in our cluster to be able to complete this challenge. And then we can just, divide that by, we have 10 regions, divide that by 10 and ask for that capacity in each region. And this graph here sort of shows that distribution of different instance types across different regions. Some regions gave us all of the exact same instance type. Others had it much more spread throughout. It's kind of just whatever slack capacity was available at the time. And we were able to ramp this up quite quickly. This graph here shows the amount of time it took all 6,100 of those instances to register and be marked as schedulable in Nomad. And I'll note that this was far slower than what Amazon was actually able to provide us instances at. Once we hit go and everything spun up at once, I think all of those instances seemed to launch within the first minute or so. It was quite quick. And then Nomad sort of works through the backlog of those connecting and coming online and did it in just right around 6.5 minutes. All right, so I touched a little bit on how EC2 Spot utilizes spare capacity and that spare capacity could be needed again. The way this works is that Amazon will send a interruption notification, and 2 minutes after that notification has been issued, it will terminate the instance regardless. You have no say in this. And so today, if you were just to run Nomad on EC2 Spot, the way this would look is Amazon would send that interruption notification, and then 2 minutes later, terminate the Nomad instance. And the Nomad server would see that. It would see that that node has disappeared for some reason, and it would reschedule its work elsewhere in the cluster, which is really great. Nomad's really great at handling those failures and moving workloads to where there's spare capacity. But this is not a completely desired situation. Suppose that you have workloads running on this terminated instance that that were handling requests and maybe needed to migrate requests onto a different allocation, or maybe it had some sort of state it wanted to back up gracefully as it was shutting down. we, that's undesirable for the workloads running here. Well, Nomad has a draining feature built in where you can target a node and drain that node, and it will work through all the allocations on that node, shut them down gracefully, allow them to complete any shutdown logic they need, and then spin them up elsewhere. So as part of this, I'm really happy to announce that we actually built an integration with AWS Spot to be able to receive those interruption notifications in Nomad and then be able to immediately start draining the node. This also works with Amazon's. They have a rebalance recommendation, which is similar to an interruption notification, but if EC2 Spot is able to detect that capacity is shrinking, it will send a preemptive recommendation to move to a different instance type. This lets us increase that window from 2 minutes potentially to a few more minutes to give more time for the node to drain. So this was really exciting. It's something that we've been working on as part of these challenges. It is not open source yet, but it will be very soon. So what did we learn in all of this? Personally, I learned a lot of operator empathy for folks who run Nomad at large scales, specifically in observability of the scheduler. I think anyone who's ran Nomad in production has probably ran into the, why is my job stuck in pending? It's just stuck there. What is going on? And even for myself, who has been working on Nomad for almost 3 years now, that is not always a very easy question to answer. There's always an answer, but it's often not easy to get to. So for me, this sort of opened my eyes. So we really need to be providing more observability into what the scheduler is doing and why it's in the state that it's in. The other thing is server sizing. I often get the question of, well, how large should my Nomad servers be to handle XY workload? And it's very hard to make that recommendation. And so having a better idea of how to do that is something else as well. Let's look at the server sizing that we used for this challenge. So this is a graph of the memory usage profile as we progress through this test. And this is not in percentage, this is in number of gigabytes used. These instances actually have somewhere upwards of 480 or so gigabytes. So we were well under the memory threshold of this instance. But again, it's really nice to see a very linear graph here. It's a little choppy as we go through snapshots and other processes which write state out to disk. But overall, it's a very linear growth in terms of number of allocations the cluster is managing over time. And this is what our CPU graph looks like. Now, the CPU was kind of a tricky one because of the instances we ran on, I think, had 32 CPUs. And by default, Nomad will spin up a worker process for the number of CPUs you have to make scheduling plans. And once those scheduling plans are made, they're submitted to the leader to be serialized and accepted. Well, we had so many workers working on so many scheduling plans that we'd often get quite a backlog of plans that needed to be applied. And if you know anything, or if you've ever worked with optimistic concurrency, the longer you sort of wait, the more out of date the information is, and the plan ends up rejecting the leader ends up rejecting quite a few plans. So we had to tune the number of workers a little bit for this, and it's something we want to document and sort of produce something for those findings later. But one other thing I wanted to touch on is interesting bugs that we came across. This was my favorite one as we were early on, as we just started spinning things up and running them. I ran into one of those situations where it's why is the scheduler not making any progress? Everything's just stuck in pending. And after some debugging, I dumped some profiles of what was going on. This specifically was a go routine profile. So this tells us, instead of how much CPU time is being used, it's a profile of how many go routines are currently part of each function call. And in this profile, I found 18.5 million go routines stuck in this deployment watcher function, which is the deployment watcher in Nomad is a utility that watches a deployment's progress and updates the state back to the state store. So this was definitely a bug and something that no one else would probably run into at most scales, but something we're able to find and harden Nomad even more as part of this. Like I said, all of these results are published on hashicorp.com/C2M. You can also view the 1 million container challenges at /C1M if you'd like.